What if today is the same as yesterday? Can you escape when time itself is your prison? What if every choice you make resets the moment you make it? Would you even know if you were living the same day forever? This isn't time travel. This is time trapping you. This is not a story of time travel. It's a story of being trapped in time. And now, the loop begins. Have you ever experienced that peculiar sensation when time seems to stretch and fold upon itself? When a moment feels both new and eerily familiar? Perhaps it was just as the morning light filtered through your window, casting those same patterns across your floor. Or when your fingers traced the weathered edge of an old photograph, and suddenly, you were there again, not remembering the moment, but living it once more. What if I told you that these whispers of recognition might be more than just tricks of the mind? What if time itself has been here before? Imagine waking up to the same sunrise, again and again, a day that loops, a universe that circles back. It sounds impossible, but in the strange world of physics, it is not. Tonight, we explore the silence between seconds, the mirror inside the moment, the possibility that we are trapped in a time loop. Time, we measure it, spend it, waste it, and chase it. Yet we rarely question its fundamental nature. We assume it flows in one direction, like a river moving inevitably towards some distant sea. Forward, always forward, from past to present to future. But what if this most basic assumption is merely an illusion? What if time is not a line but a circle? Not a journey, but a return. The clock on your wall marks off seconds with mechanical precision. Tick, tock, each moment dying as the next is born. But in the depths of quantum physics and the curves of Einstein's spacetime, those rigid boundaries begin to blur. Here, in this twilight realm between what we know and what we question, time behaves with surprising flexibility. Consider how time already bends in your everyday experience. When you wait anxiously for news, minutes stretch into painful eternities. When you lose yourself in moments of joy, hours compress into fleeting seconds. If time can feel so malleable in our perception, might it be equally flexible in its physical reality? The ancient Greeks pondered this. They gave us two words for time: chronos and kairos. Chronos is measured time, the steady march of seconds and years. Kairos is lived time, the depth and meaning within a moment. Perhaps these two faces of time hint at a deeper truth. That time is not what we think it is. In the quiet darkness of night, when the world falls away and thoughts drift like clouds across a vast inner sky, we sometimes feel the edges of time soften. Memory and anticipation bleed together. Past conversations replay with new endings. Future moments seem strangely remembered rather than imagined. Could these liminal experiences be glimpses of time's true nature? Physics tells us that at the quantum level, time behaves with unsettling ambiguity. Particles seem to know their future paths. Effects can precede causes. The clean separation between now and then dissolves into a quantum soup of probability and potential. Meanwhile, in the vast theater of the cosmos, Einstein showed us that gravity curves not just space, but time itself. Near massive objects, or at tremendous speeds, clocks run slower. Time stretches. If gravity can bend time, could it bend it all the way around, creating a closed loop? Closed time like curves, the physicists call them, paths through space-time that eventually return to their starting point, not just in space, but in time as well. They exist in the mathematics of general relativity. These strange loops, are they merely mathematical curiosities? Or could they represent something real? If time can loop, what would it mean for us, creatures who experience existence as a continuous flow? Would we be aware of the repetition? Or would each cycle feel entirely new? Our memories reset with each turn of the cosmic wheel. Some philosophers have long contemplated the eternal return, the idea that all configurations of matter and energy must eventually repeat, given infinite time, that this exact moment, with you listening to these very words, has happened before and will happen again. Not as similar moments, but as the exact same moment, played out in endless recursion. Does that thought comfort or disturb you? To know that your joys might be relived infinitely, that your sorrows are not unique to this iteration of time, that the choices you agonize over may have been made by you countless times before, or perhaps time loops in smaller cycles, not the entire universe repeating, but localized islands of recursion, moments caught in temporal eddies, days that refuse to end, lives that circle back to critical junctures. The closed circle of time invites us to question the nature of cause and effect. If an effect can loop back to become its own cause, then what initiated the loop in the first place? What exists outside the circle? Is there an outside at all? These questions hover at the edge of human understanding, where physics meets philosophy, where mathematics touches mystery. They ask us to reconsider our place in a universe that might be far stranger than our linear minds can easily grasp. As we drift deeper into this exploration of time loops, release your attachment to certainty. Allow yourself to wonder, to question, to imagine time not as the straightforward path you have always known, but as something more complex, something that spirals and folds and occasionally returns to where it began. In the coming chapters, we will walk gently through the science, the speculation, and the profound implications of cyclical time. We will examine what physics tells us is possible, what philosophy suggests is meaningful, and what it would mean to live within the embrace of a moment that never truly ends. So settle in, breathe deeply, and listen as we unravel the nature of time itself. Perhaps you have heard this all before. Perhaps this is the first time. Or perhaps, in the strange reality of a looping universe, it is somehow both at once. The journey ahead may challenge everything you thought you knew about past and future, about choice and destiny, about the very fabric of reality. But it begins, as all journeys must, with a single step, a single moment. This one, right now. Are you ready to question time itself? These traditions suggest that the purpose of existence within such cycles might be to recognize the cycle itself, to awaken to the nature of reality and thereby transcend it. Perhaps this is what science, myth, and spiritual tradition all point toward, that time loops exist not as traps, but as opportunities for deepened awareness. In physics, time loops challenge our understanding of causality. In philosophy, they question our conceptions of choice and meaning. In spiritual traditions, they offer metaphors for awakening and transcendence. Across these domains, the image of time folding back upon itself serves as a powerful tool for reconsidering our place in the cosmos. A time loop, then, is more than just repetition. It is a reconfiguration of reality itself, a different way of organizing the relationship between events, a challenge to our assumption that time must always move forward, that causes must always precede effects, that once a moment passes, it can never return. As we lie here, contemplating these recursive patterns, our own thoughts loop back upon themselves. Ideas circle and return, approached from different angles, seen in different lights. This is the nature of reflection, of consciousness observing itself. Perhaps time loops are simply the universe engaging in a similar process of self-reflection, circling back to examine what it has been. What is a time loop? It is a question that invites us to reconsider everything we thought we knew about time itself. To question whether our perception of linear progression might be an illusion created by limited consciousness. To wonder if, perhaps, we have asked this question before, and will ask it again. As we move forward in our exploration, remember that whether or not physical time loops exist, the concept itself loops through human thought, recurring across cultures and eras. It persists because it speaks to something essential about our experience of reality, something that feels simultaneously impossible and somehow true. Time loops may remain theoretical, mathematical curiosities in the equations of physicists, or They may be the fundamental structure of reality itself. Either way, contemplating them changes how we understand our place in the flow of time. And in that contemplation, we create our own kind of loop. A circle of thought that returns us, changed, to where we began. In such a scenario, time loops would be manufactured rather than naturally occurring. They would be technological achievements rather than cosmic phenomena. Perhaps advanced civilizations have already developed such technology. Perhaps humanity itself will one day master the manipulation of space-time, creating controlled environments where closed time-like curves allow limited forms of time travel. The energy requirements would be enormous, the technical challenges formidable. Yet we should not assume that what seems impossible to us now will remain impossible forever. The history of science and technology is largely a history of transcending apparent limitations. Even if we never harness closed time-like curves for practical time travel, understanding their theoretical possibility transforms our conception of reality. It reveals time not as a rigid, one-way street, but as a potentially flexible dimension capable of looping back upon itself under the right conditions. This understanding connects with ancient intuitions. Many pre-scientific cultures conceived of time as cyclical rather than linear. The ancient Maya tracked vast temporal cycles, spanning thousands of years. Greek cosmology included concepts of eternal return. Hindu traditions describe cosmic cycles of creation and destruction, called kalpas, each lasting billions of years. These mythic time cycles differ from the closed time-like curves of physics, yet they speak to a similar intuition that time might not be the simple forward progression we commonly experience. That deeper patterns might exist, patterns of return and recursion operating on scales beyond ordinary perception. Modern physics has given mathematical form to these ancient intuitions. Einstein's spacetime, warped by mass and energy, allows for the possibility that time loops back upon itself, that the future might connect to the past, not through reversal, but through continuation along a curved path through the four-dimensional continuum. If we could somehow perceive the full structure of spacetime, rather than experiencing it moment by moment, we might see these loops as natural features of the cosmic geometry. We might recognize that linear time is a local phenomenon, like the illusion that the Earth is flat when we can only see a small portion of its curved surface. Just as a circle appears as a straight line to an ant crawling along a small segment of its circumference, the potential loops of time might appear as linear progression to beings who experience only a limited portion of their extent. Our perception of past, present, and future as distinct and sequential might be an artifact of our limited perspective. What would it mean to expand that perspective? To perceive time not as flowing, but as an existing dimension we move through. Einstein himself noted that for physicists, the distinction between past, present, and future is a stubbornly persistent illusion. In the equations of relativity, all of time exists at once, a complete dimension rather than a flowing process. If time loops, this perspective becomes even more profound. The future would not just exist alongside the past in a static four-dimensional block. It would connect to the past, forming a closed system where beginning and end unite. The universe would not have a linear history, but a circular one. Not a story with a first page and a last page, but one where the last page leads directly back to the first, to be read again and again. Would we be trapped in such a loop, doomed to repetition without possibility of change or growth? Not necessarily. Even within a closed time-like curve, variation could exist. Quantum uncertainty might introduce small differences with each iteration. Over time, these differences could accumulate, creating distinct paths through the same looping temporal structure. Imagine a record playing on a turntable. Each rotation brings the needle back to the same point on the vinyl, yet the music continues to evolve and develop. The loop is physical, a circular path, but the content experienced along that path changes. Perhaps cosmic time loops function similarly, with physical structure repeating while the events playing out within that structure evolve. Or perhaps consciousness itself provides a way to experience time loops differently with each iteration. If awareness can somehow transcend the physical constraints of spacetime, it might maintain continuity across loops, remembering previous cycles and approaching each repetition with new perspective. As we contemplate these possibilities, we float in the strange intersection of physics and philosophy, where mathematical equations give form to questions about the fundamental nature of existence. Whether or not closed time-like curves physically exist in our universe, the fact that they emerge naturally from our best theories of space-time suggests that reality is far more flexible, far more mysterious than our everyday experience indicates. Time may or may not loop in the physical sense described by general relativity, but in contemplating the possibility, we expand our understanding beyond the linear progression that dominates ordinary perception. We open ourselves to a universe where time itself might fold and curve, where the path to the future might sometimes lead back to the past, and where the distinction between beginning and end might ultimately dissolve in the perfect unity of the circle. Perhaps true liberation from time loops comes not through struggling against their boundaries, but through recognizing a dimension of being untouched by temporal cycling, not by breaking the loop, but by awakening to what was never trapped within it. Not by manipulating entropy, but by realizing an aspect of consciousness independent of thermodynamic constraints. This approach aligns with wisdom traditions that emphasize acceptance rather than resistance, recognition rather than control. If you discover yourself within a time loop, perhaps the thermodynamically optimal response is neither desperate struggle nor passive repetition, but mindful presence that transforms your relationship to the cycle itself. In quantum mechanics, observation affects the systems observed. In thermodynamics, measurement generates entropy. In time loops, awareness itself might be the catalyst that transforms temporal structure, not through energy expenditure or entropy manipulation alone, but through the quality of attention brought to each recurring moment. As we drift now between thoughts of thermodynamics and awareness, between entropy's arrow and time's potential loops, feel the stillness that underlies all movement, the quiet center around which all cycles turn, the peace that remains unchanged whether time flows forward, loops back, or dissolves entirely into the eternal present. In this stillness, we find not answers, but perspective, not escape, but acceptance, not control, but harmony with whatever temporal patterns we inhabit. Whether trapped in loops or carried along linear progression, consciousness itself remains the witness, the experiencer, the knower of time's unfolding mystery. What is a time loop? The question itself feels circular, inviting us to trace its edges with our minds, to follow its curve back to where we began. In its simplest form, a time loop is a segment of time that repeats itself. A moment, a day, a year, perhaps even a lifetime that cycles back to its origin point and begins again. But this definition only scratches the surface of a concept that challenges our most fundamental understanding of reality. Time loops exist in our stories. The ancient symbol of the Ouroboros, the serpent consuming its own tail, represents the eternal cycle of death and rebirth. In Norse mythology, the world serpent Jormungandr encircles the earth, its body forming an unbroken loop around reality itself. These images speak to a deep intuition that perhaps time is not the straight arrow we perceive, but something more recursive. But what would a time loop truly mean in physical terms? To understand this, we must first understand what distinguishes a genuine loop from a mere cycle. The seasons change in predictable patterns. Winter yields to spring, spring to summer, summer to autumn, and autumn back to winter. This cycle has repeated for billions of years on our planet. But each winter is distinct from the last. The atoms and molecules have rearranged. The world has changed, however subtly. This is a cycle, not a loop. A true time loop would mean the exact same configuration of matter and energy returning. Not just similar circumstances, but identical ones down to the position of every subatomic particle. The same thoughts would form in your mind. The same words would leave your lips. The same light would fall across your face, in precisely the same way. Would you know if you were caught in such a loop? Perhaps not. If your memories reset with each iteration, each cycle would feel like the first and only time. You would make the same choices, feel the same emotions, live the same life, with no awareness of repetition. This raises a profound question. If a time loop occurs, but leaves no trace in memory or consciousness, does it matter that it loops at all? Consider the film Groundhog Day, where the protagonist relives February 2nd repeatedly. This fictional representation captures something essential about how we conceptualize time loops. There, the character retains his memories while the world around him resets. His consciousness provides continuity across the discontinuity of time. But is this how a real time loop would function? Physics suggests otherwise. In the equations of Einstein's general relativity, time is not separate from space. They form a unified continuum called space-time. Just as space can curve and fold, so too can time. And just as you can follow a path through curved space that eventually returns to its starting point, mathematics allows for paths through space-time that loop back upon themselves. Physicists call these closed time-like curves. A closed time-like curve would allow you to return to a previous moment in your timeline, not by traveling backwards, but by moving forward along a loop that eventually connects with its past. Imagine walking around a circular track. You never change direction, always moving forward, yet eventually return to where you began. A closed time-like curve functions similarly, but in 4 dimensions rather than 2. But here we encounter the first of many paradoxes. If you can return to a previous moment, what prevents you from changing that moment? And if you change it, how could you have arrived there in the first place to make that change? This is the infamous grandfather paradox, where a time traveler prevents their own birth, and thus could never have existed to travel through time at all. Theoretical physicists have proposed solutions to these paradoxes. The Novikov self-consistency principle suggests that any trip through a closed time-like curve must be consistent with the history that led to it. You could visit the past, but would find yourself unable to change events in ways that would create paradoxes. The universe would constrain your actions to maintain consistency. But time loops need not encompass your entire timeline. Imagine smaller recursive structures in time, moments that repeat locally while the larger flow continues. These would be like eddies in a river, where water circles back temporarily while the current moves forward. Some have suggested that déjà vu, that uncanny feeling that you have experienced a moment before, might be a glimpse of these temporal eddies. A glitch in our perception, where for an instant, we become aware of repetition. But this remains speculation, more poetry than science. In computing, loops are fundamental structures. Programs use loops to repeat operations without rewriting the same code multiple times. A loop begins, executes its instructions, then returns to the beginning to repeat until some condition is met. Could reality function similarly? Could the universe itself be a kind of program with loops in its execution? This brings us to simulation theory. The proposal that our reality may be a sophisticated computer simulation created by some advanced civilization. If we do live in a simulation, time loops become not just possible, but perhaps even likely. Just as video games reset when players fail, or repeat certain sequences based on programmed conditions, our reality might contain similar structures. But we need not venture into such speculative territory to find loops in our universe. Feedback loops exist throughout nature. Weather patterns react to their own effects. Ecosystems balance through cycles of growth and decline. Even our consciousness loops back upon itself in reflection. These natural cycles hint at a universe that is inherently recursive, where effects become causes which produce the same effects, where patterns repeat across scales from the quantum to the cosmic. Perhaps time loops are simply the purest expression of this recursive quality. What would it mean to experience a time loop? To live the same period repeatedly? Would it be a prison or an opportunity? In fiction, time loops often serve as vehicles for growth and transformation. Characters learn from each repetition, retaining knowledge even as circumstances reset. But would a physical time loop allow for such development? The answer depends on the nature of consciousness. If consciousness is purely physical, a product of atoms and energy arranged in specific patterns, then it too would reset with each loop. Each iteration would be experienced as if for the first time. But if consciousness transcends the physical in some way, perhaps it could maintain continuity across loops, preserving memory and awareness. Quantum mechanics offers intriguing possibilities here. At the quantum level, particles exist in states of superposition, occupying multiple positions simultaneously until observed. Some interpretations of quantum theory suggest that consciousness itself plays a role in collapsing these superpositions into definite states. If so, perhaps consciousness shares something of the quantum's ability to transcend ordinary physical constraints. There are those who claim to have experienced time loops subjectively. During intense meditation, psychedelic experiences, or near-death events, people report sensations of time folding back upon itself, moments expanding to contain eternities, the boundary between now and then dissolving. Are these merely alterations in perception, or glimpses of time's true nature? Perhaps most profound is the question of meaning in a looping universe. If time circles back, if all events repeat, what significance do our choices hold? Does free will exist in a reality where every decision has been made before and will be made again? Or does the loop itself constitute a kind of determinism, where choice is illusory? Yet meaning might exist precisely in our relationship to the loop. Even if events repeat exactly, our awareness of this repetition could change. Each loop experienced as unique from the perspective of consciousness, even if physically identical. The meaning would lie not in changing what happens, but in how we relate to what happens. Consider the concept of eternal return proposed by philosopher Friedrich Nietzsche. He asked us to imagine living the same life over and over for eternity, unchanged in every detail. Would this be heaven or hell? His answer: it depends on how we live. If we embrace each moment fully, live with purpose and acceptance, then eternal repetition becomes not a burden, but an affirmation. The loop transforms from prison to paradise through our relationship to it. Here we touch upon the spiritual dimensions of time loops. Many religious and philosophical traditions conceive of time as cyclical rather than linear. Hindu cosmology describes vast cycles called kalpas, where universes are created, exist, and are destroyed, only to be created anew. Buddhist concepts of samsara portray beings cycling through incarnations until achieving enlightenment. The wheel of time turns and returns. Where does time come from? Before Einstein, the answer seemed obvious. Time was absolute. A universal clock ticked at the same rate for everyone, everywhere. A second for you was identical to a second for me, regardless of our circumstances. Time flowed steadily forward, an invisible river carrying all of existence from past to future. But in 1905, Einstein published his theory of special relativity, and this comfortable notion of time shattered. Time, it turned out, was not absolute at all. It stretched and compressed depending on relative motion. Two observers moving at different speeds would measure different durations for the same event. A clock in motion runs slower than a stationary one. Not as an error of measurement, but as a fundamental property of reality itself. Then came general relativity in 1915, expanding this revolution in our understanding. Time was not just relative to motion, but to gravity as well. Near massive objects, time slows down. The stronger the gravitational field, the more pronounced this effect. Clocks at different altitudes tick at different rates. The clock on a satellite orbiting Earth runs faster than an identical clock on Earth's surface, requiring constant adjustment to maintain synchronization. These are not theoretical abstractions. They are measurable facts. GPS satellites must account for both special and general relativity to function correctly. Without these adjustments, location errors would accumulate at a rate of about 10 kilometers per day. Every time you use a mapping application on your phone, you're experiencing the practical effects of Einstein's revelation about the malleable nature of time. But Einstein's equations revealed something even more profound. Time and space are not separate entities, but aspects of a unified whole called space-time. Just as we cannot separate the length, width, and height of an object, we cannot truly separate time from the three dimensions of space. They form a four-dimensional continuum, a single fabric upon which the drama of the universe unfolds. In this conceptual framework, time becomes spatial in a sense. We can visualize it as a dimension extending perpendicular to the familiar three dimensions of space. The past lies in one direction along this dimension, the future in the other, with the present as a three-dimensional slice moving along the time axis. If time is a dimension similar to space, might it share other properties of space? Could it curve? Could it form closed paths? In three-dimensional space, we can easily imagine circular paths that return to their starting points. What would it mean for a path through four-dimensional space-time to do the same? This is where the concept of closed time-like curves emerges. In the language of relativity, a time-like curve is the path an object takes through space-time, always moving forward in time. If such a path can loop back to its starting point, not just in space but in time as well, we have a closed time-like curve. The mathematics of general relativity allows for such structures. In 1949, the logician and mathematician Kurt Gödel discovered a solution to Einstein's field equations describing a rotating universe where closed time-like curves were not just possible, but inevitable. In Gödel's universe, all matter rotates around a central axis. This rotation warps space-time in a way that creates paths looping back through time. Gödel showed his solution to Einstein himself. The great physicist was troubled by the implications. If his equations allowed for time travel, perhaps something was missing from the theory. Or perhaps time travel was physically possible after all. Other solutions followed. The Van Stockham dust, a theoretical cylinder of rotating matter that creates closed time-like curves in its vicinity. The Tipler cylinder, a massive, infinitely long object spinning rapidly enough to drag space-time into loops. The Kerr metric, describing the space-time around a rotating black hole, where loops through time might exist within certain regions. More recently, theoretical physicist Kip Thorne proposed the possibility of traversable wormholes that could connect distant points in space-time. By manipulating one mouth of such a wormhole, these connections could potentially form closed time-like curves, allowing for travel into the past. All of these solutions share common elements. They involve extreme conditions, enormous masses, rapid rotation, exotic matter, with negative energy density. None are easy to create or access, yet they exist as valid mathematical solutions to the equations governing our universe. But mathematics allows many things that physical reality might forbid. Do these solutions represent genuine possibilities, or merely artifacts of equations pushed beyond their domain of validity? Stephen Hawking proposed what he called the chronology protection conjecture, suggesting that the laws of physics would somehow conspire to prevent closed, time-like curves from forming. Perhaps quantum effects would intervene, creating insurmountable energy barriers. Or perhaps some yet undiscovered principle makes time loops physically impossible, despite their mathematical existence. The question remains open. No definitive proof has emerged that closed time-like curves cannot exist in our universe, nor have we observed any evidence that they do. We inhabit an uncertain middle ground where time loops remain theoretically possible, but practically unverified. Let us imagine, though, what it would mean to encounter a closed time-like curve. Unlike the fictional time machines of popular culture, you would not vanish from one moment and appear in another. You would not experience time running backwards. From your perspective, you would move continuously forward, following a path through space-time that eventually returns you to a previous moment. This raises profound questions about causality and free will. If you could return to a previous moment, could you change the past? The mathematics suggests no. Any action you take upon returning would be part of the same consistent timeline that led you to make the journey in the first place. The loop would be self-consistent. You would not remember having been there before, because from the perspective of your personal timeline, you had not been. This concept of self-consistency resolves the grandfather paradox, where a time traveler prevents their own birth. In a closed time-like curve, such a paradox could not arise, because any action taken in the past would already be accounted for in the history that produced the time traveler. You could not change what had already incorporated your presence. Imagine a pool table with 6 pockets. A ball enters pocket 1, then emerges from pocket 6, rolling across the table and into pocket 1 again. From the ball's perspective, It moves continuously forward, never reversing direction. Yet it travels a loop. This is analogous to movement along a closed time-like curve. The key difference is that on a pool table, the ball enters pocket 1 before it exits pocket 6. In a closed time-like curve, causality becomes circular. Events are both causes and effects of themselves. The ball enters pocket 1 because it exited pocket 6, and it exits pocket 6 because it entered pocket 1. Neither comes first in any absolute sense. This circular causality challenges our intuitions, but not necessarily logic itself. In mathematics, recursive definitions and circular references can be perfectly consistent. Perhaps the universe functions similarly, with loops of causality forming closed systems within the broader flow of time. If closed time-like curves exist, they would most likely occur in extreme environments, near the event horizons of rotating black holes, within the cores of extremely dense neutron stars, in the first fractions of a second after the Big Bang, when space-time itself was compressed into a quantum foam of fluctuating geometry. These environments lie far beyond our direct experience, yet we can study them through observation and theory. Astronomers track the behavior of matter near black holes. Particle physicists recreate conditions similar to the early universe in massive accelerators. Cosmologists develop mathematical models of how space-time itself behaves under extreme conditions. Through these studies, we may eventually determine whether closed time-like curves are genuine features of our universe or mere mathematical curiosities. Either answer would profoundly impact our understanding of reality. But time loops need not encompass the entire universe to exist. They might form locally, creating regions where time curves back upon itself while remaining linear elsewhere. Theoretical physicist Ronald Mallet has proposed that intense circulating light beams might warp spacetime enough to create tiny, localized time loops. Have you ever wondered if the universe itself hesitates? If reality pauses at the crossroads of possibility before choosing its path forward? If at the smallest scales, time behaves not as a flowing river, but as a shimmering sea of potential moments, collapsing into definite form only when observed? These questions carry us into the strange realm of quantum mechanics, where the rigid certainties of classical physics dissolve into probabilities and paradoxes. Here, in this microscopic domain, time reveals aspects of its nature invisible at larger scales. Aspects that suggest our conventional understanding of temporal progression, of before and after, cause and effect, may be incomplete. Quantum mechanics emerged in the early 20th century, when physicists discovered that subatomic particles do not behave according to Newton's laws. Matter at its smallest scales exists in states of possibility rather than definite position and momentum. Until measured, a particle exists as a probability wave, potentially located at many points simultaneously. This is not merely uncertainty about where the particle is, but a fundamental property of reality itself. The particle genuinely exists in multiple states at once, a condition called superposition. This quantum superposition challenges our intuitive understanding of reality. How can something be in two places at once? How can Schrödinger's famous cat be simultaneously alive and dead until observed? These paradoxes feel almost magical, as if the universe operates by different rules when we're not looking. But what does this have to do with time? With loops and paradoxes in the temporal fabric, the connection lies in how quantum mechanics treats causality, the relationship between cause and effect that seems to define time's arrow. Consider the double-slit experiment, perhaps the most famous demonstration of quantum weirdness. When individual particles like electrons or photons are fired one by one through two parallel slits, they create an interference pattern on the detecting screen behind, as if each particle passes through both slits simultaneously and interferes with itself. This suggests each particle exists in multiple locations at once. But what happens if we place detectors at the slits to observe which one each particle passes through? Something remarkable occurs. The interference pattern disappears. Each particle now behaves as if it passed through only one slit. The mere act of observation changes the outcome. This phenomenon, where measurement collapses quantum superposition into definite states, raises profound questions about time and causality. Does the observation in the present somehow influence the particle's past behavior, or does the particle somehow anticipate future observation and adjust its behavior accordingly? Physicist John Wheeler proposed a thought experiment called the delayed choice quantum eraser that pushes this temporal strangeness further. In this experiment, the decision to observe which path a particle takes can be made after the particle has already passed through the slits. Yet this later choice still determines whether the particle behaves as if it went through one slit or both. The implications are dizzying. It appears as if the future measurement reaches backward in time to influence the particle's past behavior. As Wheeler himself put it, the present has a hand in shaping what we call the past. This apparent backward causation brings us to the concept of retrocausality, where effects precede their causes. In quantum mechanics, several phenomena suggest this possibility. Quantum entanglement, where particles separated by vast distances maintain instantaneous connections, can be interpreted as involving information traveling backward in time. When we measure one entangled particle, we instantly know properties of its partner, regardless of distance, without information needing to travel between them at the speed of light or slower. The physicist Richard Feynman developed an interpretation of quantum mechanics where particles can be viewed as traveling all possible paths between points, including paths that move backward in time. In his path integral formulation, a particle going from point A to point B takes every possible route simultaneously, with each path contributing to the probability of the particle arriving at B. Some of these paths involve the particle briefly traveling backward in time. In Feynman's quantum electrodynamics, when a positron, the antimatter counterpart of an electron, travels forward in time, it can be mathematically described as an electron traveling backward in time. This mathematical equivalence suggests a fluidity to temporal direction at the quantum level. These quantum phenomena do not prove that macroscopic time travel or time loops exist, but they do reveal that at the quantum level, time behaves with surprising flexibility. The clean separation between past and future that we experience in our daily lives blurs. Cause and effect become entangled in ways that challenge our intuitive understanding of temporal sequence. If time at the quantum scale permits such strangeness, might these effects sometimes extend to larger scales? Could quantum temporal phenomena occasionally manifest in ways we could directly experience? Some theorists suggest that quantum effects might indeed allow for macroscopic temporal anomalies under certain conditions. The concept of quantum tunneling illustrates how particles can seemingly defy classical limitations. In tunneling, particles pass through energy barriers they shouldn't have enough energy to overcome. It's as if they borrow energy from the future to surmount the barrier, then pay it back after passing through. This temporary violation of energy conservation reveals how quantum mechanics permits brief departures from classical constraints. Could similar quantum phenomena allow for brief violations of temporal constraints? Might particles, information, or even consciousness occasionally tunnel through time as well as space? The many worlds interpretation of quantum mechanics, proposed by Hugh Everett III, suggests that each quantum measurement creates a branching of reality, with all possible outcomes occurring in separate, parallel universes. In this view, what appears as probability in our single universe is actually certainty spread across multiple realities. If the many worlds interpretation is correct, then in a sense, time loops already exist. Every possible configuration of particles, every possible sequence of events, exists somewhere in the vast branching structure of the multiverse. From this perspective, a time loop would simply be a particular path through this branching structure that eventually reconnects with its starting point. This brings us to the quantum mechanics of time paradoxes. Classical time travel scenarios often lead to logical contradictions, such as the grandfather paradox, where a time traveler prevents their own birth. But quantum mechanics offers potential resolutions to these paradoxes. The physicist David Deutsch proposed that quantum mechanics could resolve time travel paradoxes through its inherent probabilistic nature. In his model, a time traveler attempting to prevent their own birth would find their actions constrained by quantum probability. They might fire a gun at their grandfather, but quantum fluctuations would ensure the bullet misses. Or they might succeed in killing their grandfather, but this would occur in a parallel universe, with the time traveler now existing in a reality different from their origin. The Novikov self-consistency principle, which we touched upon earlier, finds support in quantum mechanics. According to this principle, time loops can exist, but can only permit events that are self-consistent. Paradoxes are avoided not through external constraint, but because only consistent histories have non-zero probability of occurring. Quantum mechanics provides mathematical machinery for calculating these probabilities. In the consistent histories approach developed by Robert Griffiths and others, quantum systems are described by sets of histories, each with assigned probabilities. In this framework, paradoxical histories, where cause and effect form irreconcilable loops, have zero probability. They simply cannot occur. This quantum resolution of time paradoxes suggests that while time loops might exist, our fear of logical contradictions arising from them is unfounded. The universe would naturally select only those looping histories that maintain consistency. But the quantum approach raises new questions. If multiple histories exist with different probabilities, who or what selects which history actually occurs? Does consciousness play a role in this selection, as some interpretations of quantum mechanics suggest? Or is our universe simply one manifestation of countless possible histories, all equally real from some higher dimensional perspective? These questions lead us to the role of the observer in quantum mechanics, one of the most controversial aspects of the theory. In the Copenhagen interpretation, observation causes quantum superpositions to collapse into definite states. But what constitutes an observation? Does it require conscious awareness, or simply physical interaction with a measuring device? If consciousness does play a special role in quantum mechanics, as some physicists like Eugene Wigner and John Wheeler have suggested, then the relationship between mind and time takes on new significance. Perhaps consciousness itself exists partially outside the constraints of linear time, capable of influencing quantum probabilities across temporal boundaries. This would align with certain subjective experiences that suggest consciousness sometimes transcends ordinary temporal limitations. Precognitive dreams, where people report accurately foreseeing future events. The sense of knowing who is calling before answering the phone. The feeling that time slows down during accidents or emergencies. While these experiences are often dismissed as coincidence or illusion, they persist across cultures and throughout history. Could such experiences reflect a genuine quantum connection between consciousness and time? Might our minds sometimes perceive across the probabilistic web of quantum possibilities, glimpsing potential futures before they manifest? The scientific evidence remains inconclusive, but quantum mechanics at least allows for the possibility that consciousness interacts with time in ways classical physics cannot explain. The phenomenon of quantum entanglement suggests another possibility, that time itself might be an emergent property rather than a fundamental dimension. In entangled quantum systems, particles share a single quantum state regardless of distance. When measured, their properties correlate instantly, faster than light could travel between them. This instantaneous connection appears to violate Einstein's special relativity, which prohibits faster than light communication. But entanglement does not transmit usable information faster than light. Instead, it suggests that, at a deeper level, the separated particles remain fundamentally connected, as if distance, and perhaps time, are in some sense illusory. Some theoretical physicists, including Julian Barber, have proposed that time does not exist as a fundamental reality, but emerges from quantum entanglement between systems. In this view, what we experience as temporal flow is actually the manifestation of quantum correlations between different configurations of the universe. Time would be not a dimension we move through, but a measure of how quantum states relate to each other. If time emerges from quantum relationships, rather than existing as an independent dimension, then time loops would represent particular patterns of quantum correlation that circle back upon themselves. Not paths through a pre-existing temporal dimension, but self-reinforcing networks of quantum connection. This perspective aligns with certain approaches to quantum gravity, the ongoing effort to reconcile quantum mechanics with general relativity. In theories like loop quantum gravity, space-time itself is quantized, composed of discrete units at the Planck scale, about 10 to the negative 35 meters. At this incredibly tiny scale, the smooth continuum of spacetime dissolves into a quantum foam of fluctuating geometry. In this quantum foam, temporal relationships might become as flexible and probabilistic as other quantum properties. Microscopic time loops might form and dissolve, creating a complex temporal structure from which our experience of linear time emerges at larger scales. The physicist Roger Penrose has suggested that quantum effects might occasionally influence macroscopic systems through a process called orchestrated objective reduction. In his model, quantum superpositions in the microtubules of brain cells collapse not randomly, but according to a deeper quantum gravitational process. This could potentially connect human consciousness to fundamental aspects of spacetime, including temporal structure. If Penrose is correct, our conscious experience might sometimes access quantum temporal phenomena directly. Our sense of now, of the present moment, might be more than just a psychological construct. It might reflect a genuine interaction with quantum time, where past, present, and future exist not in rigid sequence, but in dynamic superposition. This brings us to perhaps the most profound temporal paradox of all: the measurement problem in quantum mechanics. When we observe a quantum system, its wave function appears to collapse instantly, selecting one outcome from many possibilities. But what causes this collapse? And how does it propagate through space faster than light? Some interpretations, like the transactional interpretation proposed by John Cramer, suggest that quantum measurements involve a handshake across time. A wave propagates both forward and backward in time, with the future measurement reaching back to meet the past preparation of the system. The collapse happens not at a specific moment, but across the entire temporal interval, connecting future and past in a single quantum transaction. If correct, this would mean that quantum measurements create their own kind of time loops, microscopic connections between future and past that bypass the conventional flow of time. Every observation would involve a tiny temporal circuit, a loop through which information flows both forward and backward. These quantum time loops would be too small and subtle to notice in daily life, but they would form the hidden temporal infrastructure of reality, the quantum foundation upon which our experience of linear time rests. The mathematics of quantum mechanics allows for even more exotic temporal structures. The quantum delayed choice experiment can be extended to create what physicist Yakir Aharonov calls quantum superpositions of causal order, where the sequence of events A and B exists in superposition. Event A can both precede and follow event B simultaneously, until observation collapses the superposition into a definite temporal order. In 2019, physicists at the University of Queensland demonstrated a version of this effect in the laboratory. They created a quantum switch where a single photon experienced two operations, A and B, in a superposition of both possible orders, both A then B, and B then A simultaneously. The photon behaved as if it experienced both temporal sequences at once. These laboratory demonstrations remain limited to microscopic systems, but they reveal that at the quantum level, even the order of events, the very sequence that defines temporal progression, can exist in superposition. The distinct line between before and after blurs into quantum possibility. If quantum effects can place the order of events into superposition, might larger-scale temporal sequences sometimes exhibit similar quantum behavior? Could macroscopic time loops form through quantum processes that temporarily lift events out of conventional temporal sequence? The theoretical possibilities are tantalizing, but current evidence suggests that quantum temporal effects remain confined to microscopic scales. Decoherence, the process by which quantum systems interact with their environment and lose their delicate superpositions, prevents quantum weirdness from propagating to macroscopic scales under normal conditions. Yet decoherence itself is not fully understood, and exceptions might exist. Rare configurations where quantum temporal effects extend their reach into our direct experience. The boundaries between quantum and classical, microscopic and macroscopic, remain incompletely mapped. Perhaps the temporal paradoxes permitted by quantum mechanics serve a purpose. Perhaps they provide necessary flexibility in the fabric of reality, allowing the universe to navigate around potential contradictions and maintain logical consistency, even when causality threatens to loop back upon itself. If so, then quantum mechanics would not merely allow time loops, but actively manage them. It would provide the mathematical and physical framework through which loops in the fabric of time can exist, without tearing that fabric apart with paradox and contradiction. As we drift through these quantum possibilities, we begin to sense a universe far stranger and more flexible than our everyday experience suggests. A universe where time is not a rigid track, but a quantum landscape of possibility, where past and future connect through subtle threads of probability, where loops in time need not violate logic, because the quantum nature of reality already incorporates the possibility of such loops in its fundamental structure. Whether or not macroscopic time loops exist, quantum mechanics reveals that time itself is not what we thought. It is not an absolute flow, carrying all of existence from past to future. It is a more subtle, more flexible aspect of reality, connected to probability, observation, and perhaps even consciousness, in ways we are only beginning to understand. As we sleep, our minds drift between moments, memories of the past mingling with anticipations of the future. Dreams unfold with their own temporal logic, sometimes looping, sometimes jumping between disconnected scenes. Perhaps in this twilight state, we touch something of time's true nature. Perhaps we briefly sense what quantum mechanics mathematically describes: that time is not a line, but a landscape, not a river, but an ocean, with currents that sometimes circle back upon themselves in the eternal dance of cosmic possibility. What does it mean to be aware of time? To feel its passage, to remember what came before, to anticipate what lies ahead. If time itself were to loop, would consciousness loop with it? Or might awareness somehow transcend the cycle, carrying memories across iterations that physics claims should be forgotten? These questions bring us to the intersection of time loops and consciousness, perhaps the most mysterious frontier in our exploration. For it is only through consciousness that time becomes experience rather than mere mathematics. Only through awareness that the abstract dimension gains meaning and emotional resonance. Consider what it means to experience time. Unlike space, which we perceive simultaneously through our senses, time arrives in the narrow window of the present moment. We cannot directly perceive the past or future. We can only remember what has been and imagine what might be. Yet somehow, consciousness weaves these memories and anticipations together with present perception to create our sense of temporal continuity. This subjective experience of time differs markedly from the objective time measured by clocks. When we are engaged in enjoyable activities, hours seem to pass in minutes. When we are bored or in pain, minutes stretch into hours. During sleep, hours may pass with no subjective experience of duration at all. Time, as lived rather than measured, is inseparable from consciousness itself. Neuroscience tells us that our perception of time emerges from complex processes in the brain. Different neural systems track duration at various scales, from milliseconds to hours to years. These systems synchronize and calibrate themselves through experience, creating our internal clock. But this clock is malleable, subject to attention, emotion, body temperature, and countless other variables. If our experience of time depends so fundamentally on these neurological processes, what would happen to that experience in a physical time loop? Would our neurons reset with each iteration, erasing all memory of previous cycles? Or might something in consciousness resist this reset, maintaining continuity across the loop? The phenomenon of déjà vu offers an intriguing parallel. In these strange moments, we feel with uncanny certainty that we have experienced the present situation before. Everything seems familiar, predicted, as if we are reliving, rather than living the moment. Yet we know rationally that the experience is new. Neurologists generally explain déjà vu as a temporary glitch in memory processing. The brain mistakenly flags a new experience as a memory, creating the illusion of repetition. But could some instances of déjà vu represent something more? Might they occasionally be genuine glimpses of time's circular nature, moments when the veil between iterations thins enough for consciousness to sense the repetition? Similar questions arise with phenomena like precognitive dreams. where people report accurately foreseeing future events during sleep. While skeptics attribute these to coincidence or selective memory, the persistence of such experiences across cultures and throughout history gives us pause. If time sometimes loops or folds, allowing future and past to connect, might consciousness occasionally perceive these connections during dream states when rational filters are lowered? The ancient concept of eternal return suggests a cosmos that repeats its entire history infinitely. Friedrich Nietzsche explored this idea not as a scientific hypothesis, but as an existential thought experiment. If you were told that every moment of your life would repeat exactly, eternally, how would you respond? With horror at the inescapability of suffering, or with joyful affirmation of life in all its aspects? Nietzsche's question highlights a crucial aspect of consciousness in relation to time loops. Even if the physical universe and our bodies repeated identically, the meaning we assign to that repetition could transform the experience entirely. Consciousness adds a layer of interpretation that transcends the physical facts. This interpretive capacity relates to what philosophers call phenomenal consciousness, or qualia, the subjective, first-person experience of reality. The redness of red, the painfulness of pain, the sense of now, these aspects of experience seem irreducible to physical processes alone. They constitute the felt quality of being alive, of inhabiting time, rather than merely existing within it. If time loops physically, would qualia, these subjective experiences, loop as well? Or might they somehow maintain continuity, preserving awareness across iterations in ways that physical measurements could never detect? Some Eastern philosophical traditions suggest that consciousness can indeed transcend temporal cycles. In Hindu cosmology, the universe passes through vast cycles called kalpas, each spanning billions of years. These cycles repeat endlessly, with the universe being created, existing, and being destroyed, only to be created anew. Yet individual consciousness, through spiritual realization, can potentially escape this cycle. Similarly, Buddhist teachings describe samsara, the wheel of birth and death, that beings traverse through countless reincarnations. Liberation comes through awakening to the true nature of reality beyond conceptual thinking, beyond the conventional boundaries of self and time. In this view, ordinary consciousness is trapped in cycles, but awakened awareness transcends them. These ancient traditions suggest that consciousness exists in a complex relationship with temporal cycles. It can be bound by them, repeating patterns unconsciously, or it can awaken to them, gaining perspective that allows for new choices within the repetition, or even liberation from it entirely. Modern psychology offers parallel insights through its study of behavioral and cognitive patterns. We often find ourselves caught in loops of thought and behavior, repeating the same responses to similar situations despite intending otherwise. These psychological loops feel constraining, as if free choice is illusory and we are destined to repeat ourselves endlessly. Yet psychotherapeutic approaches from Freudian analysis to cognitive behavioral therapy share a common goal: bringing unconscious patterns into conscious awareness so they can be recognized and potentially changed. The simple act of becoming aware of a loop can sometimes be enough to step outside it, to create new possibilities within what had seemed like predetermined repetition. This psychological principle might apply to cosmic time loops as well. Perhaps awareness itself is the variable that can change across iterations. Even if physical events repeat identically, the consciousness experiencing those events might evolve, noticing patterns, gaining wisdom, developing new relationships to recurring circumstances. The film Groundhog Day illustrates this possibility. The protagonist, Phil Connors, finds himself living the same day repeatedly. Physically, the day resets perfectly each midnight, but his consciousness maintains continuity, remembering each previous iteration. This memory allows him to learn, grow, and eventually transform his experience of the repeating day from prison to opportunity. While fictional, this depiction raises a profound question about the relationship between consciousness and physical time loops. If such loops exist, might consciousness function like Phil's, maintaining continuity while the physical world resets. Might awareness serve as a bridge between iterations, preserving something of what came before? Some theoretical approaches to consciousness suggest this possibility. The philosopher David Chalmers has proposed that consciousness might be fundamental rather than emergent, a basic feature of reality like space, time, or mass. If so, it might operate according to principles partially independent from those governing physical processes. Integrated information theory, developed by neuroscientist Giulio Tononi, suggests that consciousness arises from complex systems integrating information in particular ways. These integrated states contain more information than the sum of their parts, creating what Tononi calls phi, a measure of conscious integration. Systems with higher phi have richer, more unified conscious experiences. In a time loop, physical reset might erase particular memories stored in neural connections. But if consciousness partly emerges from informational patterns that transcend specific physical implementations, something of its integrated structure might persist across iterations. The particular memories might vanish, while the quality of awareness, shaped by previous cycles, remains. Quantum approaches to consciousness offer another perspective. Physicist Roger Penrose and anesthesiologist Stuart Hameroff have proposed that quantum coherence in brain microtubules might generate consciousness. If quantum effects play a role in awareness, and quantum systems display the temporal flexibility we explored in the previous chapter, then consciousness might inherit some of this flexibility. It might exist partially outside conventional temporal constraints, including those of time loops. This connects to the phenomenon of neuroplasticity, the brain's ability to reorganize itself physically in response to experience. We know that learning and memory physically reshape neural networks, creating new connections and strengthening existing ones. These changes allow us to adapt to new circumstances and avoid repeating past mistakes. In a time loop, would neuroplasticity reset completely, or might some trace remain, some subtle alteration in how neurons connect that could carry information across the loop boundary? Even without explicit memory, might we develop intuitive responses shaped by previous iterations, feeling drawn towards certain choices without knowing why? The phenomenon of implicit memory suggests this possibility. Unlike explicit memory, which involves conscious recollection of past events, implicit memory operates below awareness. It shapes our behaviors and responses without conscious recognition of what we have learned or when we learned it. Studies of amnesia patients reveal that implicit memory can remain intact even when explicit memory is severely impaired. People who cannot remember learning a skill may still improve at performing it across sessions. Their bodies remember what their minds have forgotten. In a time loop, explicit memories might reset while implicit memory, operating through more distributed and fundamental neural systems, partially persists. We might begin each iteration feeling inexplicable attraction towards certain choices or aversion to others, guided by learnings we no longer consciously possess. This implicit guidance across iterations connects to the concept of morphic resonance proposed by biologist Rupert Sheldrake. He suggests that patterns of behavior and form resonate across time and space, creating fields that influence similar systems towards similar outcomes. While controversial in mainstream science, this concept offers an intriguing model for how information might transfer across time loop boundaries without conventional physical continuity. The relationship between consciousness and time loops also raises questions about identity and selfhood. If time loops, are we the same person in each iteration? If memories reset but some quality of awareness persists, what constitutes the continuing self? Buddhism offers insight here through its concept of anatta, or no self. This teaching suggests that what we experience as a continuous, unchanging self is actually an illusion created by linking together ever-changing moments of consciousness. There is continuity, but not permanent identity. Process, rather than entity. In this view, the question of whether we are the same person across time loop iterations becomes less pressing. Identity is fluid even within a single lifetime, constructed moment by moment rather than fixed and unchanging. The same fluidity would apply across iterations, with continuity and change coexisting. Yet subjectively, we feel ourselves to be continuous beings moving through time. This sense of continuous selfhood emerges partly from narrative. We tell ourselves stories about who we are, linking past, present, and anticipated future into a coherent, autobiographical structure. These narratives give shape and meaning to our temporal experience. In a time loop, if explicit memories reset, our personal narratives would fragment. Each iteration would begin with the same starting conditions for constructing identity. Yet if something of consciousness persists beyond specific memories, the quality of how we construct that narrative might evolve. We might tell ourselves similar stories in subtly different ways, or find ourselves drawn to new interpretations of recurring events. The human capacity for narrative extends beyond individual identity to collective meaning-making. Across cultures, we have created myths, religions, and cosmologies that give shape to our understanding of time itself. Cyclical time appears in these traditions not as a prison, but as a pattern containing meaning. In Hindu thought, the cycles of cosmic time reflect the breathing of Brahma, the creator aspect of divinity. In many indigenous traditions, seasonal and celestial cycles connect human existence to larger patterns of meaning. These cultural frameworks suggest that consciousness naturally seeks to integrate temporal cycles into meaningful narrative structures. If physical time loops exist, perhaps consciousness evolved partly to navigate them, to find meaning in repetition, to discern subtle differences between iterations that physical measurements would miss. Perhaps awareness itself is the universe's way of experiencing its own cyclical nature from within, bringing subjective meaning to objective pattern. This perspective aligns with what philosopher Thomas Nagel calls the view from nowhere, the attempt to integrate objective understanding with subjective experience. Science gives us increasingly precise models of time's physical structure, including potential loops. But only consciousness can experience what it means to exist within that structure, to feel time's passage, to confront the prospect of eternal return. The integration of objective and subjective perspectives on time loops returns us to the question of free will. If time loops physically, constraining all events to repeat, does genuine choice exist? Or are we merely actors reading the same script with each iteration, believing ourselves free while following predetermined patterns? Quantum indeterminacy suggests that even within physical loops, exact repetition might be impossible. Tiny quantum fluctuations could introduce variations that amplify across iterations. Consciousness, especially if influenced by quantum processes, might leverage these tiny openings to create genuinely new pathways through the recurring temporal landscape. This connects to chaos theory and sensitive dependence on initial conditions, popularly known as the butterfly effect. In chaotic systems, minuscule differences in starting conditions produce vastly different outcomes over time. If consciousness can introduce even slight variations between time loop iterations, perhaps through quantum influences, these could eventually lead to significantly different experiences, despite the overall repetition of physical conditions. The relationship between consciousness and time loops also raises questions about collective awareness. If time loops, does each conscious being experience it separately? Or might consciousness itself be more unified than we typically recognize, with different individuals representing aspects of a greater awareness, experiencing the loop from multiple perspectives simultaneously? Some philosophical and spiritual traditions suggest forms of consciousness beyond individual minds. Jung's collective unconscious, Teilhard de Chardin's noosphere, Hindu concepts of Brahman and Atman. These point toward awareness that transcends individual boundaries. If such collective consciousness exists, it might relate to time loops differently than individual awareness, perhaps maintaining continuity across iterations in ways single minds cannot. The possibility of continuing awareness across time loops connects to the problem of death and survival. If time loops, does consciousness continue beyond physical death by cycling back to earlier points in the loop? Might reincarnation represent not sequential lives, but different positions in a greater temporal cycle, all existing simultaneously from some higher dimensional perspective? These questions stretch our conceptual frameworks to their limits and beyond. They ask us to consider possibilities that our minds, evolved to navigate linear time at human scales, struggle to grasp. Yet the effort itself may expand consciousness, creating new capacities for temporal understanding. Perhaps the most profound implication of time loops for consciousness is the invitation to fully inhabit the present moment. If now is all that truly exists, with past and future as mental constructs, and if this now might repeat eternally, then our relationship to the present takes on cosmic significance. Mindfulness practices across spiritual traditions emphasize present awareness, the experience of now unclouded by regret about the past or anxiety about the future. In a potential time loop, such presence becomes not just personally beneficial, but cosmically aligned. To be fully conscious in each moment is to meet eternity at its point of return. If we are indeed trapped in a time loop, consciousness may be both the experiencer of the trap and the key to its transcendence. Through awareness, we might transform repetition from prison to opportunity, from meaningless cycle to spiral of evolving understanding. Whether time physically loops or not, consciousness already experiences forms of temporal recursion. In memory, we revisit the past. In imagination, we explore possible futures. In dreams, we move through temporal landscapes, unconstrained by waking logic. In meditation, we touch the timeless presence that underlies all temporal experience. Through these inner time loops, consciousness rehearses for the greater loops that may exist in physical reality. It develops flexibility, learns to navigate recursive patterns, prepares for the possibility that time itself might circle back upon its own path. As we drift now between waking and sleeping, let your consciousness float freely within time's flow. Feel its currents and eddies, its moments of acceleration and stillness. Notice how awareness itself seems both within time and somehow beyond it, witnessing passage without being entirely subject to it. In this liminal state, we touch something of time's deeper nature, not as concept, but as lived reality, not as measurement, but as experience. Here, in the borderlands of consciousness, we sense how awareness might relate to time loops, how it might both participate in cosmic cycles and transcend them, how it might carry meaning across iterations that physics alone could never describe. Sleep now with this gentle knowledge that consciousness and time exist in relationship more mysterious and beautiful than our ordinary thinking can grasp. That awareness itself might be the thread connecting moments across the great wheel of time's return. That in the quiet center of your being, something watches the cosmic cycle with calm recognition, having seen it all before, yet experiencing each moment as eternally new. Why does a cup of hot tea cool, but never spontaneously reheat? Why do perfume molecules disperse through a room, but never gather back into their bottle? Why do we remember the past, but not the future? These everyday asymmetries point to something profound about time's nature, something that may determine whether time loops are possible, and if they are, how one might escape them. This is the realm of entropy and thermodynamics, where time reveals its directional quality, its arrow that seems to fly inevitably from past to future. Unlike the laws of motion, which work equally well forwards or backwards, the second law of thermodynamics introduces a fundamental asymmetry to physical processes. Entropy, a measure of disorder or randomness, tends to increase in closed systems. Order dissipates, energy disperses, possibilities multiply. This entropic increase gives time its apparent direction. We call it the thermodynamic arrow of time. It points from states of lower entropy towards states of higher entropy, from order toward disorder, from the improbable toward the probable. The past was more ordered than the present. The future will be less ordered still. Yet this raises a profound question about time loops. If entropy must always increase, how could time possibly loop back upon itself? Wouldn't that require entropy to decrease, violating the second law of thermodynamics? Wouldn't looping time need to run backwards, at least from the perspective of entropic processes? To explore these questions, we must delve deeper into what entropy actually represents. Contrary to common descriptions, entropy is not simply disorder. It is a measure of how many different microscopic arrangements of a system correspond to the same macroscopic state. It quantifies possibilities, potential configurations, the ways energy and matter can be distributed. A carefully arranged deck of cards has low entropy because only a few microscopic arrangements produce the ordered sequence. A shuffled deck has high entropy because countless arrangements look similarly random. As the universe evolves, it naturally progresses from special, improbable arrangements toward more generic, probable ones. From the extraordinary toward the ordinary. Our universe began in an extraordinary low entropy state. The Big Bang, despite its extreme energy density, exhibited remarkable uniformity and simplicity. This initial low entropy condition is what makes the subsequent evolution of complex structures possible. Stars, planets, living beings, conscious minds, all exist temporarily within the larger flow from cosmic order toward cosmic disorder. This cosmic evolution presents a significant challenge to the concept of time loops. If the universe as a whole is moving from low to high entropy, how could it possibly loop back to its initial condition? Wouldn't that require a miraculous reversal of entropy's arrow, a cosmic reset that violates the most fundamental principles of thermodynamics? Several possibilities emerge. One is that time loops, if they exist, might operate only within limited regions of space-time, within what physicists call closed time-like curves. These local loops would function as eddies within the broader river of cosmic time, allowing for circular temporal paths, while the universe as a whole continues its entropic evolution. But even these local loops face the entropy problem. If you enter such a loop at one point and exit at the same point after traveling through it, shouldn't the entropy within the loop have increased during your journey? And if so, how could conditions at the entrance and exit be identical, as a true loop requires? Theoretical physicist Seth Lloyd has proposed that quantum effects might allow for consistency in time loops, despite entropic concerns. In his model, quantum interference between different paths through the loop could ensure that only consistent histories occur. The probabilities for different outcomes would adjust automatically to avoid paradoxes, including thermodynamic ones. Another possibility comes from considering entropy not as an absolute property but as observer-dependent. What appears as increasing disorder from one perspective might represent a different entropic pattern from another viewpoint. Perhaps time loops involve shifts in observational frame, allowing for consistent thermodynamic behavior despite the apparent reversal of temporal direction. This connects to the fluctuation theorem in non-equilibrium thermodynamics, which shows that entropy can occasionally decrease in small systems over short time periods. These entropy decreases occur naturally, though with extremely low probability in large systems. They represent statistical fluctuations rather than violations of the second law. Could time loops represent large-scale versions of these entropic fluctuations? Regions of spacetime where, through some combination of geometry and chance, entropy temporarily decreases, allowing time to curve back upon itself. The probability would be vanishingly small for macroscopic systems, yet perhaps not quite zero. Alternatively, time loops might exist not as physical pathways through existing spacetime, but as resets of universal conditions. If the universe undergoes cycles of expansion and contraction, each new cycle might begin with similar low-entropy conditions, creating the effect of a time loop on cosmic scales. The challenge here is understanding how entropy would reset between cycles, a question we will explore further in our next chapter on cyclical cosmology. For now, let us consider another aspect of the relationship between thermodynamics and time loops: the possibility of escaping a loop if one exists. If you found yourself trapped in a recurring segment of time, awareness might be the first step toward freedom, but thermodynamics might offer practical strategies for breaking the cycle. In fiction, characters often escape time loops by introducing significant changes to the repeating pattern. They make different choices, create new relationships, transform themselves in ways that somehow disrupt the loop's stability. From a thermodynamic perspective, these changes might represent entropy modifications substantial enough to alter the loop's structure. To understand how this might work, consider what physicists call phase transitions. Water transforms from solid to liquid, to gas, as temperature increases. Magnetic materials lose their magnetism above certain temperatures. Superconductors suddenly lose electrical resistance when cooled below critical points. These dramatic shifts in material properties occur when microscopic changes accumulate until the system abruptly reorganizes into a different macroscopic state. Time loops might be subject to similar phase transitions. Small changes within the loop might accumulate across iterations until reaching a critical threshold where the temporal structure itself transforms. The loop might suddenly open, branch into multiple pathways, or collapse into linear time progression. Such transformations would likely involve significant entropy changes. Breaking a time loop might require either drastically increasing entropy within the loop, effectively overwhelming its self-regulatory mechanisms, or finding ways to locally reverse entropy, creating a thermodynamic anomaly that disrupts the loop's continuation. The arrow of time points in the direction of entropy increase. If time loops exist, they must somehow accommodate this arrow, either by incorporating it into their structure or by providing mechanisms for entropy to reset at specific points. Understanding these mechanisms might provide keys for both recognizing loops and potentially escaping them. Consider how memory functions in relation to entropy. Our ability to remember the past, but not the future, aligns with the thermodynamic arrow. Memories represent physical records, neural patterns formed as entropy increases. To remember the future would require entropy to decrease, for effects to precede causes in a way that ordinary physics forbids. Yet in a time loop, one might develop what feels like precognition, memories of events that have not yet occurred in the current iteration, but were experienced in previous cycles. This apparent memory of the future would not violate thermodynamics if it represented traces preserved from earlier iterations, rather than genuine temporal reversal. Such memories might provide leverage for breaking the loop. By acting on information from previous cycles, one might introduce variations substantial enough to trigger the phase transitions we considered earlier. Knowledge itself becomes a thermodynamic resource, a way of locally reversing entropy by applying information preserved across iterations. This connects to the concept of entropy in information theory, where it measures uncertainty or unpredictability in a message. Lower information entropy means more predictability, more pattern, more order. Higher information entropy means more surprise, more randomness, more disorder. In a time loop, each iteration might begin with the same physical state, but progressively diverge through the accumulation and application of information. Though physical entropy would increase within each cycle as thermodynamics demands, information entropy might decrease across cycles as patterns become recognized and leveraged. This informational advantage might eventually provide escape velocity from the loop's gravitational pull. Another approach to understanding the relationship between thermodynamics and time loops comes from considering reversible processes. In theory, some physical processes can run equally well forwards or backwards without entropy increase. These reversible processes require ideal conditions with no friction, no heat dispersion, perfect efficiency. What if the largest loop of all is the universe itself? What if cosmos follows cosmos in endless succession, each universe born from the ashes of its predecessor? These questions bring us to our final exploration, where we contemplate not just loops within time, but time itself as one great cycle, eternally returning. The notion of a cyclical universe has ancient roots. Hindu cosmology describes kalpas, vast cycles lasting billions of years, each containing the birth, life, and death of a universe. The Mayan calendar tracked great cycles spanning thousands of years. Greek Stoic philosophers proposed the ekpyrosis, a cosmic conflagration that would consume the world before it was born anew. These intuitions of cosmic renewal have found surprising echoes in modern cosmology. While the prevailing Big Bang theory initially suggested a universe with a definite beginning and, perhaps, an eventual end, several theoretical models now propose more cyclical possibilities. These models suggest that our universe may be one iteration in an endless sequence, or perhaps one bubble in a greater multiverse where universes continually form, expand, and eventually give way to new creation. The Big Bang marked the beginning of our observable universe approximately 14 billion years ago. From an incredibly hot, dense state, space-time itself began expanding, cooling as it grew, allowing matter and energy to organize into the structures we see today: galaxies, stars, planets, and eventually, life capable of contemplating its own origins. For decades, cosmologists debated whether this expansion would continue forever or eventually reverse. The discovery of dark energy in the late 1990s suggested that expansion is actually accelerating, making a spontaneous reversal seem unlikely. Our universe appears destined to expand indefinitely, growing ever colder and more diffuse as stars burn out and black holes eventually evaporate through Hawking radiation. This heat death scenario presents a seemingly linear destiny, a one-way journey from the ordered simplicity of the Big Bang to the disordered simplicity of maximum entropy. Yet within this apparent linearity, several theoretical models propose mechanisms for cosmic renewal, ways the universe might loop back upon itself at the largest scales. The cyclic model, developed by Paul Steinhardt and Neil Turok, suggests that our universe exists on a brane or membrane in higher dimensional space. This brane periodically collides with a parallel brane, with each collision triggering a new Big Bang. In this model, the universe undergoes endless cycles of expansion and collision, with each collision wiping the slate clean and generating conditions similar to those we associate with the Big Bang. Another approach, the conformal cyclic cosmology proposed by Roger Penrose, suggests that the far future of one universe becomes mathematically identical to the Big Bang of the next. As matter decays completely into radiation in the remote future, the universe loses all sense of scale. This scalelessness creates conditions mathematically equivalent to those of the Big Bang, allowing the end of one cosmic aeon to seamlessly become the beginning of another. The bouncing universe models propose that when matter reaches a certain critical density during contraction, quantum gravity effects generate a repulsive force that causes the universe to bounce rather than collapse into a singularity. This bounce initiates a new expansion phase, creating a new universe with characteristics determined by conditions during the previous contraction. These models address a significant challenge for cyclic cosmologies: how to explain the low entropy state at the beginning of each cycle. If entropy must always increase according to the second law of thermodynamics, how could the universe reset to the extraordinarily ordered state necessary for a new cycle to begin? Various mechanisms have been proposed. The Steinhardt-Turok model suggests that entropy increases within each cycle, but is effectively diluted by the expansion between cycles, allowing for renewed order. Penrose's model proposes that when all matter has decayed into radiation, the distinction between large and small disappears, effectively resetting entropy counting for the next aeon. Perhaps most intriguing is the possibility suggested by quantum cosmology that new universes might form with variations in their fundamental constants and initial conditions. If these variations occur through quantum processes, they might produce universes with different properties, some more conducive to complexity and life than others. Our universe, with its particular capacity for generating complexity, might represent one iteration in a vast cosmic exploration of possible physical laws. This connects to the concept of cosmic natural selection proposed by Lee Smolin, where universes that produce many black holes have more offspring universes, as each black hole might generate a new universe with slightly varied properties. Over many generations, universes would evolve toward conditions that maximize black hole production, which coincidentally might also favor conditions suitable for life. These models transform our understanding of cosmic history from a linear progression to a vast loop, or perhaps a spiral, where each iteration shares similarities with previous cycles, while introducing new variations. The universe becomes not a one-time event, but an ongoing process of renewal and transformation at the grandest scales. If we inhabit such a cyclic cosmos, what might it mean for our understanding of time and existence? Would each cycle truly repeat, or would each new universe represent a genuine creation with its own unique trajectory? Would anything of previous cycles persist, or would each reset be complete? The mathematics of these models suggests that while broad patterns might repeat, the specific details of each cycle would differ. Quantum fluctuations would ensure variation between iterations. The cosmic loop would not be a perfect circle, but a spiral, returning to similar conditions while continuously evolving. This cosmic perspective invites us to consider our place within such vast cycles. If our universe is one iteration among countless others, does this diminish the significance of our brief lives? Or does it place our existence within a greater context of ongoing cosmic creativity, where the patterns we discover and the consciousness we embody contribute to an evolving universal story? Perhaps most profound is the realization that in a cycling universe, nothing truly ends. Forms dissolve and transform, but the underlying reality continues its dance of becoming. Stars die, but their elements seed new creation. Species become extinct, but life finds new expressions. Civilizations fade, but consciousness reawakens in new forms. The universe itself may end, but only to be born anew. This perspective offers a kind of cosmic optimism, not the naive hope that our particular forms will persist unchanged, but a deeper recognition that transformation itself is the universe's fundamental nature. The lotus of creation continually emerges from the mud of dissolution, not despite, but because of the endless cycle of change. As we drift now in the space between waking and dreaming, between the personal and the cosmic, feel the rhythms of renewal that permeate existence at every scale. The breath that flows in and out, the heart that contracts and relaxes, the mind that focuses and releases, the consciousness that awakens and sleeps. All partake in the great pattern of cosmic cycling, the eternal loop that is not a prison, but the dance of being itself. As our journey through the mysteries of time loops draws to a close, we return to the question that has guided our exploration. What would it mean if time were not a line but a circle? Not a path with beginning and end, but a cycle of eternal return? Would such a reality be a prison from which we should seek escape? Or might it offer a strange kind of grace, an opportunity to experience existence not once, but countless times? Throughout human history, we have grappled with time's nature. We have created calendars to track its passage, clocks to measure its flow, rituals to mark its significant moments. We have developed myths and philosophies that conceive of time as linear or cyclical, progressive or recurring. We have built mathematical models that reveal time's relativity, its quantum peculiarities, its thermodynamic arrow. Yet for all our efforts to understand time objectively, our most immediate experience of it remains deeply personal. We feel time passing. We remember the past. We anticipate the future. We inhabit the precarious present that seems to slip away even as we notice it. This subjective dimension of time gives meaning to whatever objective structure it might possess. If time loops, what would we notice? Perhaps nothing at all. If the loop resets our memories completely, each iteration would feel like the first and only time, with no awareness of repetition. The loop would exist mathematically, physically, but not experientially. From the inside, it would appear as linear as any conventional timeline. But what if something persisted across iterations? What if some trace remained? Some feeling of familiarity? Some intuitive knowledge of having been here before? What if consciousness maintained continuity, even as physical circumstances reset? Then the loop would become not just a structure, but a journey. Not just a pattern, but a path of potential awakening. Consider how we might change if we lived the same life again and again, gradually becoming aware of its recurring nature. What would we notice first? Perhaps moments of intense significance, experiences so powerful they leave impressions deep enough to survive the loop's reset. A profound love, a devastating loss, a moment of transcendent beauty or insight. These might be the first memories to break through, the first hints that time is not what it seems. As awareness grew across iterations, how would our choices change? Would we become more experimental, trying different paths through the same circumstances now that the stakes seem reduced by repetition? Or more intentional, refining our responses to recurring situations with deepening wisdom and compassion? Would we grow bored with familiarity, or discover that within repetition lies infinite subtlety, endless variation within the recurring pattern. Some might view a time loop as a kind of hell, a cosmic imprisonment in the same circumstances without hope of escape or progress. The Greek myth of Sisyphus, condemned to push a boulder up a hill only to watch it roll down again for eternity, captures this fear of meaningless repetition. Yet, as philosopher Albert Camus observed, even Sisyphus might find meaning in his task if he embraces it fully, if he makes the endless struggle his own. Perhaps a time loop would offer similar opportunity. Not freedom from repetition, but freedom within it. Not escape from circumstance, but transformation of our relationship to it. Not breaking the cycle, but breaking through to its deeper significance. The loop becomes not punishment, but practice. Not prison, but path. Others might see in a time loop a kind of heaven, a chance to perfect existence through repetition. The same joys experienced not once but countless times. The same connections formed and deepened across iterations. The same beauty encountered with ever-fresh appreciation. Like a beloved piece of music that reveals new depths with each listening, a recurring lifetime might disclose its subtle harmonies only through many returns. This perspective aligns with philosopher Friedrich Nietzsche's concept of amor fati, love of fate. He proposed that the highest affirmation of life would be to will its eternal recurrence, to embrace each moment so completely that one would choose to live it again and again forever. Not from resignation to necessity, but from such profound love of existence that one would refuse to change a single detail. Whether heaven or hell, the loop would be what we make of it. Its meaning would emerge not from its structure alone, but from our conscious relationship to that structure, from the quality of awareness we bring to each recurring moment, from the intentions we form within repetition, from the love or resistance we offer to eternal return. If we are indeed living in a time loop, whether personal or cosmic, individual or universal, what might we notice? What subtle signs might reveal time's circular nature? Perhaps the feeling of déjà vu, that uncanny sense of having experienced a moment before. Perhaps patterns that recur across different scales, fractal similarities between small and large cycles. Perhaps intuitive knowledge that emerges not from teaching, but from recognition. Wisdom that feels remembered rather than learned. Or perhaps we would notice nothing obvious at all. Perhaps the loop would manifest not as supernatural experience, but as natural law, as the physical principles that govern reality. The conservation of energy, the patterns of growth and decay, the cycles of celestial bodies, the rhythms of life and death, the eternal dance of form, emerging from formlessness and returning again. These natural patterns suggest that even if time as a whole does not loop, aspects of reality certainly do. Day follows night, follows day. Seasons cycle through their ancient sequence. Tides rise and fall with lunar rhythm. Planets orbit stars, which in turn orbit galactic centers. From heartbeats to brainwaves, from circadian rhythms to menstrual cycles, our bodies themselves embody time's recurring patterns. Perhaps these nested cycles within seemingly linear time offer a key to understanding loops at larger scales. Perhaps what appears as straight-line progression from sufficient distance reveals its circular nature when viewed more intimately. Perhaps cosmic time, like the curved space of Einstein's relativity, only appears flat within the limited frame of our ordinary perception. If we could somehow step outside time, perceiving it as we perceive space, all at once rather than moment by moment, what pattern would we see? A line stretching from past to future? A circle returning to its starting point? A spiral that both returns and progresses? A branching structure of possibilities, some looping back, others continuing into new territory? Or something more complex still, a hyperdimensional geometry beyond our capacity to visualize? Whatever its ultimate structure, our journey through time remains deeply personal. Whether it loops or not, how we inhabit each moment determines its quality, its meaning, its beauty. Whether we live once or innumerable times, the present moment is where consciousness meets reality, where potential becomes actual, where life is actually lived. If time loops, we may never know with certainty, but in every breath, in every heartbeat, in every return of attention to the present moment, we feel its echo. the pulse of existence, the rhythm of being, the gentle oscillation between forgetting and remembering who and what we truly are. Maybe we are meant to live it over. Maybe we are meant to notice. Or maybe this is the first time. Sleep now, in the arms of time. Whether it flows forward, circles quietly back, or transcends all direction in the eternal present, you are held in its embrace. Rest in the knowledge that whether or not time loops, consciousness continues its journey of awakening, of discovery, of love. And if you should wake tomorrow to the same sunrise, the same world, the same life you have known before, perhaps you will feel not imprisonment, but possibility, not repetition, but renewal, not the weight of eternal return, but the lightness of beginning again, with fresh appreciation for the miracle that is this moment, this breath, this precious opportunity to be alive and aware within time's mysterious flow. Sleep now, dreamers, in the gentle rhythm of cosmos and consciousness, in the quiet space between seconds, in the timeless awareness that witnesses all temporal change. Whether tonight is unique in cosmic history or one iteration among countless others, it is yours to experience, to embrace, to inhabit fully. Time may or may not loop, but life, precious life, is happening now, and now, and now.